Hi guys, and welcome to a new video course about linear algebra. So we're going to jump into our first topic, which is linear systems and systems of linear equations. So a linear equation is any equation that can be written in this kind of format, where you have some coefficient times some variable plus some other coefficient times some other variable plus as many variables as you want. Let's say you have n variables. And all of this is equal to some number. So let's see an example of a linear equation. So in this case, we see that we have 1 times x, which matches this format. Then we have minus 1 times y, and then we have a3 being 2, and then our x3 is z, and then we have our a4 term as 1, and then our x4 term as w, and then all of this is equal to some real number. In this case, it's 4. So this equation here aligns with this format of a linear equation. Thus, this one is considered a linear equation. So let's see something that's not a linear equation. Well, one example could be, say, x squared plus y equals 2. This equation right here is not a linear equation because we can't rewrite it in some format where we have some number times x plus some other number times y equaling some number. We can't convert this equation into this format. Thus, this one is not considered a linear equation. Now, going back to our example that is a linear equation, we can create a system of linear equations, which is one or more linear equations that all have the same variable. So I'm going to turn this one linear equation into a system of linear equations by adding this second equation. So now these two equations, they both use the same variables, so we can put them together and create a system of linear equations. Now you may be wondering, what if our second equation instead looked like this? Is this still considered a system of linear equations? Well, the answer is yes, even though this one has 4 variables and this one has 3 variables. In this one, we can just consider that we set our a4 number to be 0 times x4. So both this and this are systems of linear equations. So now we can talk about a solution to this system. Now, a solution to a linear equation is usually written in this kind of format, where you have a bracket, then you have some number, then you have comma, some other number, comma, as many variables as you have, let's say of n variables, and then you close the bracket. So, how you would interpret this, if this right here is a solution to some linear equation, what it means is when you take all of these s numbers and you plug them in to their respective variables, so let's sub in s1 for our first variable, then we sub in s2 for our second variable, and so on. And then now that we're just multiplying and adding a bunch of constant numbers together, we can go ahead and evaluate this. And if this right here is indeed a solution, we should get that this equals C. this number over here. So we can see an example of that with this system up here, where we have 1, 0, 2, minus 1 as a solution. And you'll notice that if we sub in 1 for x, 0 for y, 2 for z, and minus 1 for w, we're going to end up with 4 on this side and 4 on this side. Thus, this right here is a solution to this linear equation. And something like this is considered a solution to an entire linear system if, when you plug these same numbers into every equation, you get that all of the equations in the linear system are satisfied. And notice, one thing that's important to note is that a linear system does not necessarily just have one solution. You'll see that this right here is also a solution to this linear system. If we plug in 1 for x, 1 for y, 2 for z, and then 0 for w, we're going to get that this equation works, and then if we do the same for the second equation, this one works. So both this and this are solutions to this system of linear equations. Which brings us to the definition of a solution set, which is the set of all possible solutions to a system of linear equations. So for this example, both this and this are in the solution set to our system. And then that segues right into equivalent linear systems. So I'm going to write out a new system real quick. So here's a new system of linear equations, and we say that two systems of linear equations are equivalent when they have the same solution set. So I'm going to write out another linear system. So this system right here and this system are equivalent linear systems. And the way you can convince yourself of that is if you were to actually compute what the solution to each of these systems is, i.e. what the x, y, and z values should be. For this one thing you can notice is you can just divide every term in this first equation by 2. And you're going to end back up with this other system. So you can be pretty confident that this one and this one are going to have the same solution set. Thus, they are equivalent systems. Now, another thing to note is there are two kinds of linear systems, consistent ones and inconsistent ones. A consistent linear system is one that has at least one solution. So going back to this example, this is a consistent system because this right here is a solution. A system is inconsistent if it has no solutions. So let's consider the solution, or the system, x equals 1 and x equals 2. This is a system of linear equations, and the solution set of this system is the empty set. There's no number that we can sub into x where x equals 1 and x also equals 2. So this system right here is called inconsistent. Now let's go quickly to our next big topic, which is a matrix. So what a matrix is, I like to think of it as some kind of grid like this, where in every square of the grid you have some number. So this is the general format for a matrix. However, also note that it doesn't have to take this exact shape. You could also have a matrix that looks like this, where if you were to draw your grid on here, you would end up with a 2x4 grid. And in general, when we're talking about the dimensions of this matrix, we mean how many rows does it have and how many columns does it have. And so when we say a matrix A is an n by n matrix, or n by m matrix, what that means is A is a matrix where it has n rows and m columns. So this matrix here is a 3 by 3 matrix, and this one is a 2 by 4 matrix. Now, matrices are important because we can use them to represent systems of linear equations. So let's copy back down the system of equations we had above, and we can go ahead and convert this system into a matrix. And the way we do that is we're just looking at all of our coefficients. And these coefficients are going to be the numbers in each square of our grid of this matrix. So representing this system as a matrix, we would end up with a matrix that looks like this. So here's the matrix that represents this system. And we call this an augmented matrix. Usually, what we would do is we would draw a little dashed line here. And what this dashed line basically represents is if you were to go ahead and convert this matrix back into a system of linear equations, this is where your equal sign would go. And knowing this, we can see that not only can every matrix or every system of linear equations be converted to a matrix, every matrix represents a system of linear equations. So if I were to draw down this matrix, we can go ahead and convert this into a system of linear equations where all of these numbers are going to be the A1 terms times our first variable. Let's make our first variable x. And all these are going to be the coefficients in front of our second variable. Then we're going to have an equal sign, and these are going to be all the c terms that our variables are equal to. So we can convert this matrix into a system of linear equations, and what that system looks like is this. So, since every matrix represents a system of linear equations, we can go ahead and use all the same terminology that we can use with a system of linear equations and use it on a matrix. For example, the solution set of a matrix. When we're talking about the solution set of a matrix, what we mean is the solution set to the system of linear equations this matrix represents. We can also talk about equivalent matrices. Two matrices are equivalent if they have the same solution set, meaning the solution set to the system of linear equations represented by one matrix is equivalent to the solution set of the system of linear equations represented by a different matrix. Another thing we can do with matrices is we can manipulate them in the same way we can manipulate linear equations, which is going to bring us to our first important topic of the course, which is elementary row operations. So there are three operations that you can perform on a matrix where the matrix you get after performing that operation will be an equivalent matrix, meaning one that has the same solution set. So one of those operations is you can swap two rows of the matrix you can also multiply a row by a non-zero multiple, and you can replace a row with itself plus a scalar multiple of another row. So we can go ahead and see an example of that on this matrix right here. So this matrix, let's perform E1, and we're going to swap, say, the first row with the second row. So we're then going to end up with a matrix that looks like this. And these two matrices are equivalent. And the way you can convince yourself of this is if you were to draw out the system of linear equations that this matrix represents and the one that this matrix represents, you would have the same three equations, just the order that they're listed in is different. But that's not going to change the values that your different variables can take. Next, we can replace a row with a non-zero multiple of itself. So we can take this matrix and say multiply the first row by 2. And we're going to end up with this matrix right here, which is equivalent to the previous one. And we know that because if we were to draw out the system of linear equations that this matrix represents, and our first equation would look like this. And if we were to simplify this, we can just divide every row by 2. And now if we were to add in our other rows, and now convert this whole thing back into a matrix, we would end up with the matrix we had before we multiplied this row by 2. And then the last operation we can do is replace a row with a scalar multiple of itself plus another row. So let's replace the third row with 1 times this row. So the matrix we're going to end up with looks like this. And this matrix have the same solution set. And the reason why this one is true is because if you were to think about each row of the matrix as a linear equation, what we've done by adding 1 times this row is we're essentially adding the same thing to both sides of the equation, because we know that the way we interpret this equation is this thing equals 0. So then when we add 1 times this row to this row, we're adding 0 to both sides of the equation, which will not affect the equation. Same with adding this row. This would be the same as adding 1 to both sides of the equation, which would not affect the solution set. You'll also see that even if this was an inconsistent system, we can draw out the matrix representing this inconsistent system like this. And if we were to add, say, 2 times the first row to the second row, we would end up with this matrix. And converting this to a system of linear equations, we see x equals 1 and 2x equals 3. And we see that the solution set of this system is still the empty set. So the solution set of these two matrices is the same, thus these are equivalent matrices. So those are our 3 main elementary row operations that will keep a matrix the same. And now in our next video we're going to go into the next topic, which is how we can use these elementary row operations